Support reactions. Let's go over all the possible support reactions we can have when we are analyzing a rigid body in 3D space. We did that for 2D space. Now let's do it for 3D space. So I'm going to put it support reactions. Now these support reactions I'm going to show. I'll bring the photos to the slides. They are from your book. The version I have, it's at page 209. It listed all these figures you'll see in the slides I'll bring, and different supports that you have to deal with when you're looking at the rigid body in three-dimensional space. So let's just start. I'm going to talk about, well, there are 8 of them. So we're just going to go over them, well, relatively one by one, I would say. Let's start with the first one, or first one and second one. There you go. All right, so this is the first type I would put here, and this is the second type. Now, if you have a ball, right, the ball is between the structure you're looking at and some surface, or you have a rod. I should have a ball. So if you have a ball, like this, there are 2 surfaces. Let's say this is a fixed surface and the other one is the rigid body. Doesn't matter what happens, which direction this goes. There is only one force perpendicular along the line of action. So if I call this, we can go always with this X. If I call this Y and I call this Z, let me use a better call. If this is X, this is Y, and this is Z. And the same story here. Either there is a ball, or you have some kind of rod, whatever you have. I don't know why I have this around. And there is no friction. If there is a friction, you'll see a different story. It's a different time. You have to add another force. But if there is no friction, the only force is pretty much very similar to smooth contact, like normal force. Wherever the contact point of the ball is with the surface, the force should be perpendicular to that surface. So, as the book says, force with known line of action, perpendicular to the surface. Since you know the direction is always perpendicular to the surface, the only unknown left is the magnitude of the force. So we only have one unknown. For frictionless surface, the same. If you have some kind of a ball or part of the structure is on a surface and the surface has no friction, or the friction is very small, it can be neglected, can be ignored. The only thing you're going to end up having is just a smooth contact. So support reactions pretty much include smooth contact most cases. You can think about these as smooth contacts. Now the second type is a cable. And the same story as cable in 2-dimensional space. So whenever you have a cable or a chain or some kind of I guess cable and chain sums it up, or thread, something that is holding part of the structure. The force you're going to have is going to be in the same direction as that thread or chain or cable. So you know the direction. The force is in the force with a known line of action. That would be the force. The only thing you don't know is the magnitude. So one unknown again. All right. Let's make it a little more complicated. All right. Let me see, there are more supports. So let's look at this type of support. All right, just 1, 2. I'll call this 3. Now, this type of support, you have a roller on a rough surface. Rough surface means there is friction. I haven't talked about friction yet, but you know friction from physics. Roller on a rough surface, or a wheel on a rail. Now, if I have a roller, right, this is a roller, on a rough surface, why do I get 2 forces? Well, one of them is very similar to a ball. Right? It's from the surface to this roller. Right? perpendicular. Now the other one is, since we have frictional surface, right? It's like this. This roller cannot move in this direction. Right? If I hold it this way, so it can move in this direction, right? But it cannot move in this direction, right? Because there is friction. So this contact is preventing this roller from moving in two specific directions. One of them is towards the surface, obviously, right? The surface holding it there. And the other one is sideways motion, because there is a friction. So if you think about, maybe I have to go with the direction of the book. Let me change this XYZ to be more consistent with what the book considered. Consider that as Z, this is X, and this is Y. So you can always go with this, at least for this support. Things are confusing. So this is X, this is Y, and this is Z. So the roller is prevented from moving in Y direction, right? Not obviously it can go this way, but in one side, in one direction, wherever the surface is. And in Z direction, because of the friction. As I said, it's a rough surface. If there was no friction, we wouldn't have had this, because it can easily move around. Right? Friction is stopping it from moving in that direction. And wheel on a rail, the same story. Now, instead of having friction, and that friction is stopping this wheel or roller going sideways, now there is a rail there. And that rail is preventing the sideways motion, in this case in Z direction. So what you're going to end up having is two unknowns. You're going to have two force components. And always one of them is perpendicular to other. One is, let's say in this case, perpendicular to surface, right? And one parallel to axis of the wheel. If you look at this as the axis of the wheel, right, this is the axis of the wheel. That's always going to be the case. So we know the directions of these forces. Only unknowns are the magnitudes. All right. Fourth type. Find it. Would be either a rough surface. And if you have a rod like this, a bar like this, it's sitting on a surface, right? I can make it as horizontal as possible on a surface. Now this, the palm of my hand is a pretty good example of very surface with a lot of friction, I would say. At some point, obviously, if you apply enough force, you can move this, right, depending on how much force you apply. But in this course, or at least when you draw the free body diagram, you have to take into account the force applied to this bar, preventing it from moving in either direction. It can't go this way, it can't go this way, right? And it can't go, obviously, inside the surface, well, in a normal situation. So there are going to be three forces with known magnitudes. With unknown magnitudes. We know the direction. Well, they're all perpendicular. They're mutually perpendicular. We have the smooth contact upward, and we have the friction preventing the motion of this surface. Let me remember how did we do it. X, Y, Z. So this would be X. This would be Y, and this would be Z. So it's preventing three types of, I would say, preventing it from moving in three directions, mutually perpendicular, always. Ball and socket is the same story. I don't have that here, but you can think about it as a ball inside a socket. It can rotate in every direction. Doesn't matter, you can have rotation, but you can't move as long as the socket is fixed on a surface. X, Y, Z. Right? So in this case, again, It can rotate, so nothing is preventing this from rotating, and nothing is preventing this bar also is from rotating in every direction it wants. Remember, in 3D space, we have 3 translational direction, 3 rotational direction. Maybe I should have mentioned that before. So the general degrees of freedom in 3-dimensional space, you can move along X, you can move along Y, you can move along Z, and you can rotate around X, you can rotate around, let me hold it this way, you can rotate around Y, and you can rotate around Z. So we have 3 rotations, 3 translations, possible rotations, 3 possible translations, as long as a rigid body is not attached to anything. Think about an object in space, or I don't know, an astronaut floating around. Right? It can do either of these 6 possible motions, and a combination of either of them, or combination of all of them. Now, support, we said support in a structure prevents a specific type of motion, and now we're going through that. This rough surface prevents 3 directions, prevents the structure from moving in 3 directions. Ball and socket support prevents the structure from moving in 3 specific directions, but it doesn't prevent the rotation. Same story about the rough surface. It doesn't prevent the rotation. So you still are able to rotate. All right. So this was the 4th type. If I numbered correctly, 2, 3, 4. Yes. 5th type, I actually have an example of a ball and socket that we can take a look in a real condition, if I can find it. It's actually from the book, so I'll be able to do that. There we go. This is an example of a ball and sockets, I would say, joint. Where do you see it? I think this is taken from an earth grader, but you can probably see it in tractors and different, especially hydraulic systems that they're connected together. This is a real life, I would say, ball and socket joint. You just have to be more, I would suggest, walk around the different types of machines nowadays, pay attention. All possible supports in different machines should be one of these supports that we talked today. So let's see if we can identify them next time you walk around and look at different machines. And the structures, no matter what it is. It could be a mechanical machine, it could be a mechanical structure, it could be civil structure, civil engineering structure, whatever it is one of these supports. All right. Look at the 5th one. If I can find it. I should have 2 of them there together. So I'll call this the 5th one, and this is the 6th one. Starting with the 6th one is the easy one. That this is a fixed support in space, in 3D space. When we had a fixed support in 2-dimensional space, right, you could simplify the system structure in 2-dimensional. All the forces were in 2-dimensional. We only had, when we were removing that support, we only had 2 unknown forces. We were replacing the structure with 2 unknown forces and a moment. Now in 3-dimensional space, the story is different. Right? If you have a fixed support, it can't move in any direction, X, Y, or Z. So already 3 forces that you have to use to replace the structure, or the support, sorry. And then it cannot rotate in any direction, X, Y or Z. It's fixed here. So when you remove this fixed support in 3D space, or 3-dimensional space, when you look at the structure, you have to take into account all the possible forces or all the possible motions that this part of the structure is prevented from having. It's a very convoluted sentence. But the bottom line is, when you remove a fixed support, you have to put 3 unknown forces. The directions, well, depending on how you get your axes, you can just put X, Y, Z in any direction. Motion or translational motion in 3 directions and rotation in 3 directions. They're all prevented using a fixed support. So you have to take into account all of these 6 unknowns. This is the maximum number of unknowns you're going to get. Remember, even in two-dimensional space, the fixed support was giving you maximum possible unknowns in two-dimensional space, 3. Now here it gives you the maximum possible unknowns, 6. We also have universal joint. A good example of universal joint is a drive shaft of, let's say, front wheel car. If you've seen, or if you've looked underneath some of these trucks, I would say, you see the motion from the engine has to go to the wheels in the back. So if you have a rear wheels drive, the motion is going from, or the rotation is going from the engine to those wheels using a bunch of 2 shafts or maybe more connected using universal joints. You see, this universal joint, let me, I have actually a picture of that. That might make universal joint a little more easier to imagine, I would say. I wish I had some, but I don't really have a universal joint. So what happens is, if I take this as XY, this is probably the, I would say, not difficult, but it's harder to imagine. Now, what happens is that, well, once you have this joint, it means you can, this joint prevents the motion or rotation along, in this case, X direction. And you can't have motion in either direction, X, Y, Z. As I said, this is the harder one to imagine. I'll try to look up a video and put on discussion forum what universal joints. At least I had the most difficulty when I dealt with this joint for the first time, to imagining how this works. But if you looked at, again, the wheel drive, rear wheel drive cars, the way the power is transferred from the engine in front to the back, especially it's easier to see them in trucks because they're a little higher, you can see underneath. You will see these kind of joints. They are great because we can transfer the rotation, in that case torque, of the engine to the back in the car, of your car to rear, wheels in the back, without being worried about this shaft breaking. So the only prevention, or the only type of rotation it prevents, is rotation about, this is X-axis. And that's where you're transferring your force. Right? You're turning the shaft using the engine, and it's transferred into the wheels in the back. So when you have this type of joints, you have to remove, when you remove the joint, you have to consider 3 forces and 1 moment. So 4 unknowns. I don't think I don't think we even deal with this, but that's one type of support that you will see in real structures. Maybe one of the sample problems in the book. 5, 6. All right. Let's go to the next one. 7. Now, this is also a type of support you will see. 7. Now, this is a hinge. Right? The left one is a hinge, but the only difference between this and a hinge that you see, let's say, connecting door to the frames, when you see obviously open and closed doors, there are hinges supporting or connecting door to the frame. The only difference between this and those hinges is that this hinge has the freedom to move in this direction, in X direction. So this part can slide on the shaft, or whatever connection you want to call this rod. So if this is X, this is Y, and this is Z, what happens is that this specific hinge is preventing your structure to move in Y direction. In Z direction, obviously, it's you see this bolt, or I would say connector, that is connecting the hinge to that wall or whatever surface or big support we have, big, let's say, structure we have. So in the case of a door, imagine just the wall or the frame of the door. So it's preventing this from moving in y direction and moving in z direction. But you can have motion in y, and you can have rotation in y and rotation in z. Now, this is not a great example of, I guess that's the best way they could represent it. But whenever you hear hinge supporting radial load only, you can think about it this. Radial load would be, let me see if I can explain this. If this is the circle, right, this direction would be the radial load. This is radial. And that's why you see one Fy and one Fx, right? There's one force, could be in any direction with an unknown angle. So replacing this with two forces perpendicular. And we can have moments. It's also preventing moments. Now, the moment, if you look at this bearing support, this one probably you have seen when you're looking at the, I would say maybe the way fans are connected. Actually, I have an example of a fan. Let me see, that example might clarify a little bit at least. I'll put it small and put it here, but you can find it in your book. So it's a fan. Let me make it, try to find the best spot to put it without interfering with other stuff. All right, so it's a fan. This, you're going to have a radial force. I can use a better color here. It prevents any radial motion, radial direction, anywhere. If you think about this, look at it this way, this is radial direction. So it prevents this whatever shaft in this case moving from in a plane. So it prevents that. And that radial force, when you remove the support, is replaced by two forces in y and z. So this is x, this is y, and this is z. Right? And radial direction would be in this direction. I can do better than that. Radial direction would be in this direction. Any direction along the radius of the circle. We can make that, prevent that. And if you look at it, the only kind of rotation you have, which is the main purpose of a bearing, is the rotation along x-axis. Right? It rotates around x-axis, but it cannot rotate around z-axis. It's not supposed to, at least, and it cannot rotate around y-axis. Right? Hopefully, you see that. So when you remove these type of supports, right, you have to replace it with two force components and up to two couples, depending on if they tell you, they give you more information. Generally speaking, they should be there. All right, the last one. So much fun dealing with rigid body in 3D, right? The last one would be even more preventative supports. And that would be if you have a pin. All right, if you have a pin here, if this is x, this is y, and this is z. Now, what it does, well, if you have a pin support, right? If you have some kind of, let me see, I have a good example of pin support. I do have one from the book. So, this is a pin support in a real structure, actually. I think it's part of a tractor. At least that's what the textbook says, I believe. So, when you have a pin support, right? Look at the not the photo, but the image. You can't move in X, Y, or Z. You can rotate around Z, and you can't rotate around, why do I have two Z's here? This should be one. You can't rotate around Y, and you can't rotate around Z. The only rotation you have is in the X direction. So if you think about it, it's preventing any kind of motion except the motion, the rotational motion about X. So when you remove that support, you have to compensate for all the forces and moments or possible motions that are prevented by that support, which would be three forces, force components, and two couples. Now, this hinge is the typical hinge you see in a door. A door cannot do anything except rotation about the axis of the hinge, which in this case is X. Right? X, Y, and Z. The only rotation you get from a hinge, how can I put it? Maybe, is the rotation about the axis of the hinge. Other types of rotations or other types of motions, whether translation or rotation, are prevented by this support. So when you remove the hinge, let's say you want to draw a free body diagram of a door for some analysis. When you remove those hinges, you have to compensate for all the forces that the hinge was applying to the structure to prevent the motion from those directions. And also the bearings that are a little different from the bearing we saw in at the top when I was giving you an example of bearing for a fan. It could be one of those two, depending on how you fix it. But typically, these are the bearings at the end of a shaft. So not only they do what the previous one was doing, but also they prevent X, Y, and Z. Let's see. I don't know why I put Z. I guess old habit. This is Y, and this is Z. Oh, that was correct. So all three motions are prevented, except the rotation around the x-axis. Everything else is prevented. You can't even have this rotation in this motion along x-axis, as opposed to the previous one that probably your shaft could still move along the x-axis. You didn't probably care about fixing it. But once you're at the end of a shaft, you have to make sure that this shaft is fixed there. So whatever system you have, it's a generator, is an electric motor. You make sure that the stator, if it's an electric motor, is not sliding out and sliding in, right, when it's moving. So you prevent that motion too. Again, in those cases, when you remove this support, you have to consider the force applied from this bearing to the shaft in X direction to prevent that motion. This is the eighth. Now, I do understand that these supports are not as straightforward and easy to, I would say, remember as support reactions we had for two-dimensional space. But you can always look at them, and depending on, what type of support you have, support reaction you have, when you remove it, if you are drawing a free body diagram for a specific structure, when you remove it, you just remember to replace it with these forces.